Total distance. Our objective is to interpret integrals involving rectilinear motion, distinguishing between displacement and total distance traveled. Remember that the total change of a function on the interval a to b can be found as the definite integral from a to b of the rate of change. Therefore, the displacement, or the change in position over an interval time 1 to time 2, can be the definite integral from time 1 to time 2 of the velocity. If we want the total distance traveled over a time interval, time 1 to time 2, that would have to be the definite integral from time 1 to time 2 of the absolute value of the velocity function, because we don't want to just know the change in position where we subtract any backwards movement or any decrease in position. We want to add up all of the changes in position, whether it's an increase in position or a decrease in position. But the absolute value tells us to add all the movements, whether they are increases or decreases. Whereas here, when there is no absolute value, we add any increases in position and subtract any decreases in position. For example, number 1, a dry ice puck is pushed back and forth across an uneven surface. This is a graph of the velocity v in centimeters per second as a function of time t in seconds. Here is the graph of velocity versus time. Notice that on the x-axis we're counting 1, 2, 3, 4, etc. And on the y-axis we're counting 10, 20, 30, 40, etc. A. Determine the displacement, that's the change in position, by the puck for 0 to 10. So the displacement is the integral from 0 to 10 of the velocity function with respect to time. Now, because we're given a graph, we want to remember that this means the net area between the function and the x-axis. Anything below the x-axis, subtracting those areas. I would like to break this up into simple geometric figures. So we've got this triangle right here that has a base of 2 and a height of 40. And when we do that area, 1/2 times 2 times 40, that gives us an area of 40 for that triangle right there. Next, we could see this as a rectangle with a width of 3 units wide by 40 units tall. So that area we can think of as 3 times 40, or 120. We've got another little triangle next to it, which has a base half as long as that first one. So that's only going to be an area of 20 instead of 40. And then we can break this down here up into a little triangle, another little triangle, and a rectangle, all of which, when we compute that area, makes 10 plus 20 plus 10, or altogether 40. And then we've got one more tiny little triangle right here. We're doing our 1/2 times base times height. Remember, that's 20 units high, gives us an area of 10. Let's go ahead and compute our net area from 0 to 10. So we're going to add up everything above the x-axis. So we've got 40 going in order, plus 120, plus 20 over there. Subtract the part that's below the x-axis, minus 40, and then there's one more piece above the x-axis, plus 10. So simplifying that, if we need to, gives us 150, and that's going to be centimeters. Anytime we integrate a rate of change, it takes away that per second. So if we're doing the integral of centimeters per second, that leaves us with just centimeters. Remember, this is like a derivative, and this is the antiderivative, and therefore it cancels out that change and leaves just the centimeters. B. Determine the total distance traveled by the puck for 0 to 10. Total distance traveled is the integral from 0 to 10 of the absolute value of the velocity, because we don't want to subtract any of the decreases in position. We want to add up everything, whether it is above or below the x-axis. So unlike this one, where we had to subtract the 40 that was below the x-axis, this time we're adding everything. So 40 plus 120 plus 20 plus 40 plus 10, and that gives us a simplified value of 230 centimeters. Still centimeters because we're still integrating a rate of change. 2. An object in rectilinear motion is moving along a horizontal line with velocity v of t equals negative 3t squared minus 18t plus 15 in meters per minute for time 0 to 6 minutes. Part A, find the net displacement of the object from t equals 0 to t equals 6. Interpret the result in the context of the problem. So first of all, we see net displacement, and we want to think that means the integral of the velocity function. So we're going to set up the integral from 0 to 6 of our velocity function, 3t squared minus 18t plus 15. Integral starts and dt ends. Now we can take the antiderivative. 3t squared, antiderivative is t cubed. 18t, antiderivative is 9t squared. 15, antiderivative is 15t. We'll put our brackets to show that we're evaluating from 0 to 6, and then we'll plug in those values. 6 goes in first. 6 cubed minus 9 times 6 squared plus 15 times 6, and then we plug in 0 minus, and that's all 0 when we plug in 0. Simplifying that, the result is negative 18. Now we will interpret the result in the context of the problem. So thinking about how the problem talks about an object moving along a horizontal line, remember that when we integrate a rate of change, and in this case our rate of change is in meters per minute, the antiderivative cancels out that derivative part, so our units are just meters. So we would say that on this interval, time 0 to time 6, the object will have moved 18 meters, and the negative represents the horizontal position going to the left. So we could say something like, after moving t equals 0 to t equals 6 minutes, the object is 18 meters to the left. That's the negative part because we're on a horizontal movement of where it started or where it was at t equals 0. We want to make sure that when we interpret this, we use that time interval and we say what that sign represents and what that value is, and use proper units for both the time and that final value. B. Find the total distance traveled by the object from t equals 0 to t equals 6 and interpret the result. Anytime I see total distance traveled, I want to think about the integral of the absolute value of the velocity. So in this case, doing the integral of the absolute value, and still I'm going from 0 to 6, I have to think about how there are times where the object is moving to the right and where the object is moving to the left, and I want to add up all of those movements. So I've got to figure out, when does the object move to the right? When does it move to the left? So to do that, I'm going to start by figuring out when the object is not moving, or rather where the velocity is equal to 0. So let's take this 3t squared minus 18t plus 15, our velocity function. Setting it equal to 0, I can factor out a 3, t squared minus 6t plus 5. And then I can factor from there t minus 5 times t minus 1 and get that it's stopping at 1 and 5 minutes. So now we can figure out when it's moving to the right and the left. We'll place these t values on our number line and we'll figure out the signs of the velocity. Before 1, if I plug in a value such as 0, that's a negative, and a negative times a negative is a positive. So this object is first moving to the right. Then between 1 and 5, a value like 2 plugged in would be a negative times a positive, which is a negative. So now my object is moving left. And then after 5 minutes, positive times a positive is a positive, so it's moving right again. So because I need to add up all of those meters that are traveled, I'm going to have to switch the sign of the velocity function when the object is moving in that negative direction. So I'm going to split up this integral into 3 separate integrals. Now keep in mind that we're starting at the time 0 and ending at the time 6. So my 3 integrals, 0 to 1 for that first interval, where it's just in a positive direction anyway, so I can keep the 3t squared minus 18t plus 15. Add that to this next one. Now this one's moving to the left on the interval 1 to 5. So I need the opposite of the value I get so that I'm not subtracting those meters from this total. So the negative of 3t squared minus 18t plus 15. And then finally that last interval 5 to 6 of my velocity function, which is still 3t squared minus 18t plus 15. And now I have 3 problems in one, 3 antiderivatives, and then values to plug in. So let's proceed. The antiderivative, of course, we did this earlier, t cubed minus 9t squared plus 15. But this gets evaluated over the interval 0 to 1. The next one, now I might as well, instead of saying plus and negative, just say minus, or I could switch all those signs. And then again, t cubed minus 9t squared plus 15. This one goes 1 to 5. And then the last interval, still t cubed minus 9t squared plus 15t. Oops, I forgot the t in both of those, I just realized. We'll put those back. And that's on the interval 5 to 6. Now we do our computations where first I plug in a 1, then I plug in a 0. I'll save you from the rest of that as we know what this process is by this point. So plugging in 1 gives me a 7, plugging in 0 gives me a 0 for 7 minus 0, minus, for the one that's moving to the left, this one, plugging in a 5, gives me negative 25. Plugging in a 1 gives me 7. I subtract those. Plus, and the last interval, plugging in a 6 gives me negative 18. Plugging in a 5 gives me negative 25. As we saw, plugging in a 5 over here gives us negative 25. And then we can simplify this, and we get altogether 46. Now, we are able to interpret this result as well. Now, instead of in this one where we knew the net displacement was the change in position, or that it ended up, the object ended up 18 meters to the left, this time it's a total distance traveled. So this object traveled a total of 46 meters on that time interval. So let's write about that. The object traveled a total of 46 meters. Still, we're integrating meters per minute, which leaves us with just minutes. from t equals 0 to t equals 6 minutes. Remember, we use units for all the numbers involved in our integral. Thanks for watching.